Yeah.
So I will mainly start over. So I'm going to start talking about synaptic transmission. And as you'll see, it's very, very complicated. And one of the reasons to talk about synaptic transmission first is because when we talk about synaptic plasticity, we have to know which aspects of synaptic transmission can be modified by the brain. So plasticity in the next lecture. Okay, so we start here with, we're gonna have two neurons. So that's a neuron. This is a dendritic tree. Okay, so that's neuron one. There's another neuron with another dendritic tree, but neurons also have axons. This is an axon, and the axon will make connections onto another dendritic tree. And we want a close-up view of these connections. So here's our dendrite over here. This is a dendrite. This is a spine. And the presynaptic terminal will this is a presynaptic terminal. Okay. And this is really a blow up of this region. I took this and I blew it up. Okay, so it's expanded version of that region down there. And so this is where neurons make contact, this is where they communicate. And what I want to do is now talk about the steps that allow the neurons to actually essentially transmit voltage from one side to the other. So the first thing, of course, presynaptic neuron spikes. So I apologize for those of you who've just sat through this. So it emits an action potential, which looks like this, which travels down the axon. So spike travels down axon, eventually reaches the presynaptic terminal. Okay, so eventually it shows up down here. Let's kind of draw it like that. Makes it into a presynaptic terminal. Get rid of the arrow. And that opens voltage activated calcium, which I'll write Ca++. It's a doubly charged positive ion channels. Okay, so there are calcium channels in here. And they open when the voltage increases. So there's influx of calcium. Which causes vesicle release. Okay, inside the presynaptic terminals are lots of little vesicles. They're not very big. Each of them stores about 100,000 molecules. And when they're released, inside this vesicle is some neurotransmitter, and that spills out. So neurotransmitter so that's in yellow, spills out. Okay. And that opens channels in postsynaptic terminal. Okay, so there's some more channels back here. There are channels here. Neurotransmitter binds to those channels. That causes current to flow. Oops. Current to flow. Okay. 9. So that changes voltage. And eventually travels down to the soma. Okay, so the voltage goes to the soma. Okay, so as you can see, it's an incredibly complicated process. By the way, it's a very unreliable process. A lot of times, presynaptic action potential arrives in the presynaptic terminal and nothing happens at all. One of the things the brain presumably carefully regulates. But what I want to do now is go over these steps in a little more detail, okay? It seems like a lot, but if you think about it, once you have this picture in mind, you remember the presynaptic terminal with vesicles, postsynaptic terminal with channels, you can guess a lot of the rest of what's going to happen, okay? So we'll spend some time going over this in some detail. I'm going to start with a little bit of review of biophysics, okay? I assume this is review, although possibly in a different form than you saw it before. So from physics, we learned in physics that V equals IR. Voltage equals current times resistance, okay? That doesn't quite hold in neurons or synapses or anything with a membrane potential and ions on the outside. So if this is, let's say, the outside, and this is the inside, it could be a cell, it could be a postsynaptic terminal, it could be anything. And we have on the outside lots of ions. These are ions. On the inside, we have very few ions. So even if there's no there's no voltage difference, the voltage on both sides, the voltage on this side and that side is exactly the same, you'll get current flow. So current flows even, even if there's no voltage difference. See, that's from diffusion, right? These molecules, they can go this way, they can go that way, but they're more out there going this way than they are going that way, okay? And what that means is you don't have V equals IR, you have V minus E, it's called reversal potential, equals IR, call it RI, okay? And the reversal potential is the amount of voltage you need. So E reverse equals amount of voltage you need to keep ions from flowing. So for instance, if these were positive ions, you need a big positive voltage in here to keep them out. If they're negative ions, you would need a big negative voltage in here to keep them in. And if you switch the density, so you had more on the outside than the inside, that would switch. Okay. I assume you kind of learned about this. So typically, instead of using R, we use a 1 over G for conductances. So we write I equals G, V minus E reversal. Okay. And the kind of crazy thing is that in the brain, different ions have different reversal potentials and different conductances. So the true story is that I equals the sum on X of GX. Actually, I'm going to do sum on I of GI V minus EI. Okay. And I'm going to do one more thing. I'm going to put an XI in here. So G would be sort of the maximum conductance. And X is a variable. And typically between 0 and 1. Okay. And this is where all the sort of exciting things goes on in the brain. So you can have so Xi equals constant. That's called passive. That's of course what we're most used to in our physics classes. You can have Xi, but also Xi can be voltage dependent. So that led the Hodgkin-Huxley neurons but we're going to use the voltage dependent to open calcium channels. And you can also have Xi can be neurotransmitter dependent. Okay. And sometimes neurotransmitters are called neuromodulators, but that's what we're going to use here. So these channels, the conductance of these channels is going to be neurotransmitter dependent, on the amount of chemical in the synaptic cleft. Okay. So that's really a sort of a primer on things, and we're going to actually, at least in this case, and for these, you tend to have you tend to have some, write down some equation, dxi dt equals stuff, okay? Stuff can be dependent on voltage or neurotransmitter. Okay, so let's go back to our presynaptic terminal. A presynaptic terminal looks like this. Okay, there are some voltage-dependent calcium channels. And the reversal potential, so reversal potential E calcium equals reversal potential is approximately equal to 120 millivolts. Okay. And so these have activation curves, but around, so when action potential arrives, and so the two things you need to know about these voltage-dependent calcium channels, reversal potential is about 120 millivolts. That's one. And they're closed at rest, which is about minus 65 millivolts. Okay. But when an action potential arrives, voltage goes up to about about 0 millivolts. About 0 millivolts, and these calcium channels open. Oops. Okay. So the sole purpose of these action potentials were really to open these calcium activated, voltage activated calcium channels. When that happens, so we have an influx of calcium. Oops. So influx of calcium, which does something incredibly complicated, but its main purpose is to open these vesicles. So this is a vesicle. Green things are vesicles. And what happens when the calcium, there's some machinery that goes on that I know very little about. It's insanely complicated. It's getting to be worked out. They actually bind to things inside here. And the effect is to open a vesicle. And when that happens, neurotransmitter spills out. Okay. So that's the first step, opening of calcium channels, and so reversal potentials kind of matter, right? 120 millivolts. If the reversal potential was too low, reversal potential was at 0 millivolts, when they opened up, nothing would happen because the spike brings the voltage up to about 0 millivolts, okay? So they open briefly, influx of calcium, release of neurotransmitter, okay? So that's step one. And what I want to talk about now is step two, where channels on the postsynaptic side open. Okay. This is step one, or one of the early steps. And the step two is opening of the postsynaptic channels. So let me say a few words about that. So remember, let's go back to our brief intro on biophysics. Currents is basically some overall conductance, some variable that goes between 0 and 1, and then reverse the potential. Okay. So we're going to now talk about some equations because we all love equations. So we have I. So this is postsynaptic current. Equals G. Is a G and an X and V minus E post. Okay. And different channels, of course, have different conductances and different X's. But the equation for X is dx dt equals alpha, which depends on C. I'm gonna, at least for a while, make C red, times 1 minus X minus beta X. Okay. So this is concentration of neurotransmitter. So the concentration versus time is actually pretty fast. So if you have concentration, this is time. And on this axis, we have concentration. And this is concentration, remember, of neurotransmitter. So that's what we're calling, and this is C. C goes on this axis. And basically when the channel opens, it goes up very quickly and down very quickly. So the time scale is milliseconds or less. Okay. And when the concentration goes up, alpha goes up as well. So if you have alpha versus C, so it's kind of pretty steep. Okay. So, and so basically, if we plotted alpha versus T, alpha would also follow this kind of. So concentration is going up, alpha is going up. Maybe it lags a little bit on different scale. That goes something like this. So this would be alpha as a function of concentration. Okay. And to get sort of an understanding for the dynamics, what we're going to do is, or the shape of X of T, we're going to approximate we're going to approximate alpha versus T. So this is channel opens and channel closes. So alpha naught, the max is alpha naught, and this is channel opens. And this is channel closes. So the idea is when a channel opens, alpha goes instantly from 0 to alpha naught, and then it stays there for some time. Let's say the total time here is T channel. And then it closes. Okay. And given that we want to know how X behaves, So that's pretty easy. So channel open. We have dxdt equals alpha naught 1 minus x minus beta x equals alpha naught minus alpha naught plus beta x. Okay. And so solve this differential equation. So x equals asymptotically, it's going to reach alpha naught over alpha naught plus beta 1 minus e. Actually, let's put it to the minus alpha naught plus beta t. Okay, so that's got the right time dependence. So t equals 0. T equals 0. That's 0. It increases rapidly. So this time is t channel. Okay, and typically alpha naught is big. So x for alpha. So typically, so alpha naught is usually much bigger than beta. In which case, this is almost 1. So for times larger than 1 over alpha naught plus beta, the channel opens completely. And so we can plot it here. It basically goes up like this. So this is x of t. Actually, I put so this is x of t. And the red one is alpha. Okay, so alpha is going up very rapidly. X of t follows, and then and that's when this is alpha equals alpha naught. And then when alpha equals 0, x of t just goes to x. When alpha equals 0, this term has totally gone away. We just e to the minus beta x. And so x of t equals x at time whatever reach at t channel times e to the minus beta t minus t channel. Okay, so after this time it decays, and typically decay is a lot slower. Okay, so here it's e to the minus beta t, and here it's 1 minus e to the minus alpha naught plus beta t. Okay, so fast rise time, slow decay time. And that's pretty typical. So for these channels, the rise time and decay time are very different. Okay, so I'm going to actually, so this is sort of the anatomy of the channel opening, and this determines how much. So how much current actually flows in depends on, I have it in this page, depends on the reversal potential of the postsynaptic cell. We'll talk about that. So channels are really characterized by 2 numbers, or 3 numbers. Characterized by three numbers. Mainly characterized. Mainly, we'll see this in a little while. There's exceptions, mainly characterized by 3 numbers. So the rise time, decay time, and reversal potential. So I'm going to give you a list of the 4 major channels. So 4 major channels. In cortex, in the mammalian cortex. And there are hundreds of channels, all with different properties. So these are AMPA. So I wouldn't even bother thinking to try to remember these names. If you hang out in neuroscience long enough, they'll eventually will sink in. My first neuroscience meeting I went to, I was sitting at a poster, listening to somebody, nodding my head. At the end, I asked a friend, "What's GABA?" But you know, it's just a name, although it's where the names came from are kind of interesting. So this is the this axis is neurotransmitter. Well, I'll tell you what this axis is in a second, but these are the 4 major kinds. So first of all, T rise, how fast do they rise? T decay, how fast do they decay? And then E reversal. What did I call it on this slide? I called it, yeah, E post. So E post. So this is going to determine whether it's excitatory or inhibitory. Okay. So AMPA and GABA A are very fast. So this has rise times of around, so these are approximate, they vary, 0.1 milliseconds. Super fast, this is 0.3 milliseconds. So if you look at this picture, basically sub-millisecond, it goes up to sort of near its maximum. Okay. And decays are also pretty fast. So this is about 5 milliseconds. Everything's in milliseconds. This is also around 5. So NMDA is a lot slower. We'll see why. The rise time is a lot slower, but decay time can be really slow, 150 to 1,000 milliseconds. If you take 1 second for this to decay, GABA A is on the order of 10. It's slow decay to 200. Okay. So these 2 are excitatory, postsynaptic potential around 0. This is around -70, and this is around -100. Okay. So these are excitatory. Okay. Because the reverse potential around 0, you get lots of incoming. Oh wait, well, so sorry. There's one more thing that the reversal potential really tells you. So these are excitatory, reversal potential 0. Okay. You have massive influx of current, and these are inhibitory. So AMPA and NMDA are the sort of 2 excitatory neurotransmitters or excitatory channels. GABA A and GABA B are the inhibitory ones. And actually, I was in neuroscience a long time ago before I figured out what these were named after. These are named after antagonists. So if you take something called AMPA and dump it on AMPA channels, they open. If you take NMDA and dump it on NMDA channels, they open. Whereas these are named after the actual neurotransmitter. Okay, so in the case of GABA channels, it's actually, where's our picture? In the case of GABA, this is actually something called GABA. It's a GABA gamma emitter. I forget. You see it spelled out every now and then, but everybody refers to it as GABA. In the case of excitatory connectivity, this is excitatory channels. This is actually glutamate. So in this case, named after antagonist, but neurotransmitter is something called glutamate. Which is what's in monosodium glutamate. Oops. That's a U. Okay. And then once the channel is open, voltage current flows in, and you get voltage that goes and transmits to the soma. Okay. Okay, so let me take a break here. A lot of information. I can sort of give a recap after about 5 minutes. When I come back in 5 minutes, I'll tell you a little more about these channels and a little more about so the anatomy of an active potential of synaptic transmission. There are a couple other things that go on besides just release from neurotransmitter. Okay, so let's take a 5-minute break as usual. If you have any questions, I'll be right here. Okay, so let's go back to our picture. So actually there's two things. So the synaptic strength is really what we believe is modified when animals learn. There are actually lots of things that could be modified, but nothing else, there are more free parameters for weights than, say, single neuron properties. And second of all, that makes most sense from what we know about networks. And so there are two main things that could be modified. The obvious one is sort of the number of channels in here. So the brain could regulate the number of channels. Given the voltage dependence, it could actually regulate the type of channels in principle, and the way it does do that. It could also, you might think it could regulate the amount of neurotransmitter released. It turns out it doesn't do that. But what it does do instead is regulate the probability of release, okay? So it turns out that when action potential arrives at the presynaptic neuron, sometimes neurotransmitters release and sometimes it's not. And sometimes means it hovers around 0.5. So, I mean, it seems kind of crazy. If you look at this picture, we have relatively complicated process, axon, spike, travels down the axon, it goes to lots of different neurons. Only about half of those on average do anything. It seems like a really, a big waste of energy, and B, it adds a huge amount of noise to the system. So I want to say a few words about probabilistic synaptic release, and then we'll go on and talk about plasticity. So basically, P release, it basically is typically between 0.2 and 0.5. Actually, 0.2 and 0.8. Okay. Nobody really knows why it isn't 1. So one hint is that there is a synapse when P release is near 1, but it's huge. And it may be that just because synapses are small, they can't really have high release probability. But it has a big range, right? Why doesn't the brain, it's got a big range. So why doesn't the brain just make it as high as possible? That's not known either, but it is known it's carefully regulated. It also changes on short time scales. So if you plotted P release, there are actually two effects. So this is 0, this is 1. So if you put P release on this axis. And let's say sort of there's some background probability. Call this P naught. So what happens when there's a spike? So these are spike times. So two things happen. One is there's a brief buildup of calcium. So in some sense, pre-release goes up. So it goes up a little bit and then decays. If there's a spike here, it's actually more likely that it kind of jumps up. And jumps up again, okay? So P-release goes up, so it's called facilitation. Due to buildup of calcium. Okay. So if you go back to this picture, remember with voltage-gated calcium channels open, calcium, oops, oh no. What color is that? It's red. These are channels. So that's calcium coming in. Okay. When the voltage gated channel is open, calcium comes in. It's heavily regulated, right? Calcium is one of the most regulated, ions in the brain because it does so much stuff, and it's quickly taken up by into calcium stores, but it hangs around for a little while. Okay, and if you get two exponentials in a row, there's going to be more calcium, and what you're going to get is so this is a little buildup of calcium and a slight increase in neurotransmitter release. But that's not the only thing going on. The other thing you have is depression, and that's because of, so there's sort of one more thing you need to know. If you go to, actually, I'm going to draw a whole new picture because this is important. If you look at the presynaptic terminal, so I drew vesicles. So these vesicles aren't completely mobile. It's really only the ones down here. So this is the readily releasable pool. So RRP, readily releasable pool. And so if one of these is released, right? If one of these is released, right now there are 5 in here. If this one goes away, there are now only 4. And if a bunch of them go away, it goes way down, okay? And so if you have a bunch of action potentials, you get this decrease associated with, so there's a decrease depression associated with the fact that you have fewer vesicles in the readily releasable pool, and that, of course, only happens. This is if there's a failure. So that only happens if something's actually released. So these are so in these two spikes, so vesicles were released. Okay. On this one, no vesicles was released, so the probability of release didn't change. It's really only depletion of this. And then once they're depleted, these have to diffuse in here, and that takes time. For vesicles to diffuse into the RRP, the readily releasable pool. Okay. I mean, it's kind of crazy that this actually works. All right. So it's just these things are tiny. So the typical size of these things is, I should know this. It's a few nanometers. So the size of this is, so size equals 10 to 50 nanometers, I think. So I know that if you look at the postsynaptic neuron, so the distance to the next neuron is a few nanometers. So these are really, really small. There's also molecular machinery that has to go on. It's a miracle it works, okay? So when it comes to plasticity, the brain can control both the release probability. The other thing it can control is, let's draw another picture. So we have pre, and we have post. Okay. So probably appears to be controlled, but there's much less work on that. Most of the work is on so channels. So let's actually go back to this page. So the brain can adjust synaptic strength and does adjust synaptic strength by adjusting release probability. P0. Okay. I'm not going to talk about that much. Instead, I'm going to talk about another method. So the brain can adjust channel density. Okay. And you can imagine it can just insert channels. I mean, these channels can be added and subtracted. But there's something that should possibly have occurred to you. And let's go back to our learning rules. Okay, so when we wrote down learning rules for deep networks, actually I'm going to go over here. What did our learning rules look like? Oops. So learning rules for deep networks. Delta Wij, let's say in layer L. Actually, let's get rid of layers. Well, I'll put them in because they were there before. The change in the weights was equal to some learning rate times delta IL times xj L minus 1. So if you recall, the picture was like this. This is layer L. This is L plus 1. L plus 1. Oops. Sorry, this is layer L minus 1. This is layer L. And if you look at, one synapse, let's say this is neuron J, this is neuron I, and this is WIJL. So delta IL is a postsynaptic term. So there were two terms we needed to change to compute how much the weight should change by, and delta IL is postsynaptic. Okay, it's a property of that neuron. That neuron has access to delta IL. We don't know where it comes from. That's a backpropped error signal. But delta IL, remember, comes from the previous layer. XJL is presynaptic. Okay. So in any learning rule, if we go back to here, okay, so the spike, the arrival of the spike, so this is basically XJL. This is our presynaptic term. This is presynaptic. Okay. And now we have a problem because basically over here is a soma. So this is a soma. which is a long ways away. Okay, so these genetic trees can be pretty big, right? So you want to know what's going on. The postsynaptic term lives way over here, is over here, and these dendrites can be millimeters away. Okay, so how is it that the neurons can transmit information about what's going on in the soma all the way out here? Okay, so this distance, so distance from distance to soma can be hundreds of microns. Okay, it's pretty far. And so the brain needs some kind of coincidence detectors. And this is where NMDA channels come in. So this is basically one of the major kinds of plasticity in the brain. So the brain needs the synapse needs information about the postsynaptic, the voltage at the soma. Okay, so you actually get that something called the backpropagating action potential. So it gets that from a backpropagating action potential. Okay, so if you actually go over here, so this is sort of what's going on. Well, I mean, we can actually look in here. So I'll draw this picture. When this neuron spikes, the voltage goes up, and we think of dendrites as transmitting information from the synapses to the neuron. How when the neuron spikes, it transmits information in the other direction, right? Voltage goes out here. So the backpropagating action potential, the voltage actually, if it goes up here, you actually see this out in the dendrite. Okay. So basically, if you have draw a picture of neuron. So here's our neuron. Got some synapse way out here. So if you plot on this axis, so voltage, so V, so the voltage at the synapse, oops, what happens? So the voltage of the synapse might go, big action potential. So this is V at soma. This is versus time. This propagates along the axon, and by the time it gets to the axon, gets to the synapse, it might look, it's not as big. It's a little more spread out, but it might go like this. So at the synapse. Okay. So the voltage of soma can be transmitted to the synapse, and now all the neuron has to do is have some mechanism in which the voltage modifies its behavior. Okay, so we're going to see one more sort of very cool channel. The NMDA channel. You got to marvel at evolution. How does it come up with this stuff? Let me make sure I have all the parameters straight. Where is it? Oh, there it is. Oh. So I in MDA. So it's equals, so there's a G NMDA. Remember, this is a maximum conductance. There's an X, which is our neurotransmitter dependent term. And just to remind you, that term looks like this. So this is X. X goes up. Remember, for NMDA channels, it takes about 10 milliseconds and it goes down slowly. Okay, so X is our neurotransmitter dependent term. And then we have, as usual, V minus E NMDA, which is around 0 millivolts. So far it looks like a regular old channel, but it's got this other super cool property. It actually depends on magnesium concentration. It depends on voltage, so it's yeah. So it's 1, the usual 1, plus the concentration of magnesium, another ion in the brain is doubly charged, over 3.57 millimolar. I think it's millimolar. Minus V divided by 16.1 millivolts. Okay. So what's that look like? So if you look at the current, the NMDA current versus voltage, this is voltage. This is around minus 60, which is around rest. And we'll call this 0, reverse the potential. So if you only had, we're going to assume X equals 1. So if you only had this term, our usual term, we would get a picture that goes, something that goes like this. Okay, just goes up, up, up. Okay, so this is I NMDA. At X equals 1, when X is fully open. Okay, so this is what happens when magnesium equals 0. And there's no magnesium. So no, or let's make it easier. So Mg plus plus, let's up with this. So M G plus plus equals 0. You have no magnesium in your brain, which is a good reason to have magnesium in your brain. But if, so here's around, but if you do have magnesium, and it's reasonable, around 3 or so millimolars, this is, let's say, what do we have? So this is minus 20, minus 40. So what really happens when you have magnesium is this goes up and it rolls back down. Okay, because when V is, let's say, minus 60 over 16 is about 4. This is e to the 4th, and you get this suppression by a factor of e to the 4th. Okay. So this is the actual currents. This is so mg on the order of 3 millimolar. Okay. So what happens is that the NMDA channels don't actually open unless there's been an action potential at the soma. Okay, so this, let's go back to this picture. So the voltage here, so this is, put some numbers on here, this is minus 60. And this might be as high as minus 20. Okay. So the synapse goes to minus 20, and that allows NMDA channels to open. And the picture we should have in NMDA channels is something like this. So here's our NMDA channel. So at low voltage, we'll do low voltage in blue. So, you know, V on the order of say minus 60 millivolts. You have lots and lots of magnesium ions floating. Magnesium ions. So magnesium ions block, magnesium ion block NMDA receptors. Okay. On the other hand, when V is around, let's say, minus 20 millivolts, I mean, it's basically because these are positively charged. So magnesium, let's be clear, these are plus plus. That's what capital M is usually done. So V equals, let's say, minus 20 millivolts. You have a lot fewer magnesium ions. So in this case, magnesium plus ions largely removed. And now if you're an NMDA receptor, in the case of so look, we're going to focus on this case. So, you know, at high voltage, now when neurotransmitter arrives, I think I learned eventually. So now I can do, so when V is approximately equal to minus 20 millivolts, and neurotransmitter arrives, current flows through NMDA channels. And that caused a chain of events that leads to insertion of AMP channels. Okay, so this is NMDA. If current flows through here, stuff happens, and you get AMPA. Okay. So it's a pretty complicated chain of events, but I mean, these things, remember, are tiny, and this is what happened to evolve. Okay, and what's really, really important is that this is coincidence detection. Okay, it's got the pre and the post-synaptic voltage matter. Okay, so I think I'll end here. On Thursday, I'm going to talk about the implications of these plasticity rules. This is one kind of plasticity. There are many, and they have many different sort of phenomenological effects on synaptic strength. And we'll talk about those effects and a little bit about what we know about what plasticity does in the brain, or think we know it does in the brain. Okay, I'm very well in the beginning. Not sure what happened. Hopefully it won't happen again. And as usual, I'll stay here for a few minutes in case you have any questions.
Hello, Professor.
Oh, hi.
I don't think the student has any question. So
Okay.
yeah, I think the class is over. Yeah.
Okay, great. Thanks.
Thank you.
Bye.
Bye.